So we're going to be looking at water hardness today. This is going to be focusing on the first 2 pages and the top of the 3rd page of your notes on water in your book. This is the 3rd time I've had to do this because my surface keeps shutting down because it's overheating. So let's hope it works this time. So these are all the words we're going to be coming across for this, let's call it a lesson. So we're going to look at hard water, what temporary hardness and permanent hardness are, how soap reacts with hard water, the precipitates that are made, including limescale, and what ion exchange is, and deionizers and distilled water. So these are ways of removing hard water. So water hardness, just to begin with, it's water that doesn't easily form a lather with soap, and it's caused by having calcium or magnesium ions dissolved in the water. When those ions are dissolved in the water, what happens is that it ends up forming a scum instead of forming suds. So you need to keep adding soap until all of that calcium and magnesium is gone. And once the calcium and magnesium is gone, now you can add more soap and it will make suds. So we're going to need our flashcards here because we have a definition, and the definition is hard water on the front of your flashcard, and on the back of your flashcard it's water that will not easily form a lather with soap, caused by the presence of calcium 2+ or magnesium 2+ ions. So get that onto a flashcard and then you can move on. So basically, the more calcium and magnesium that we have, the harder the water. The less we have, the softer the water. And when we're going to do calculations later on, we're going to pretend that all the calcium and magnesium in the water is due to this chemical here, calcium carbonate. And the reason we're going to do that is because it makes our calculations nice and easy, because the molecular mass of calcium carbonate is a nice 100. It's a nice number to use. So how does soap react with hard water? So this is a soap molecule here, really big molecule, but basically this is its formula for soap. So whenever we see this, we're going to know that it's soap. So the soap will form a scum with hard water because soap normally likes to just dissolve in water and form suds. But if there's calcium or magnesium there, our calcium or magnesium, whichever one, will react with the soap and it will form this stuff here, which is soap scum. And that soap scum ends up wasting the soap. So we need to keep adding soap and keep adding soap until all of this is gone, all of the calcium. And once it's gone, the next bit of soap then will be able to form a lather with water and will be able to use for cleaning. So it actually softens the water. The soap softens the water because it removes the calcium and magnesium. So we have 2 types of hardness that we're going to look at: temporary hardness and permanent hardness. And we'll be calculating how much temporary and permanent hardness is in water. But to do that, we'll need to know something else later on, and that is total hardness. And the total hardness of a water sample is just when we take the 2 of these and combine them. So if I add them together, the temporary hardness and the permanent hardness, I'll get the total hardness of the water, and that'll be important later on. So our temporary hardness in water. We're going to start off by having a definition. So our definition of temporary hardness in water, so front of the flashcard, temporary hardness, and on the back, the actual definition itself is hardness that can be removed by boiling. So we can remove this hardness just by boiling the water. And it's caused by 2 different chemicals dissolved in the water. Either calcium hydrogen carbonate. That's an ion that we should know from our glance card. Or magnesium hydrogen carbonate. So if you see hydrogen carbonate, you know that causes temporary hardness in water. If that was anything else, like a sulfate or anything, it's not temporary hardness, only if it's hydrogen carbonate. So let's look at our water cycle. So we know that water evaporates from bodies of water, from sunlight, then moves over land, it precipitates back down to the land, and it filters down through the earth. And as it filters down through the earth, it will pick up ions. So it will pick up calciums and magnesiums from the rocks and hydrogen carbonates and other ions, and that will contribute to the hardness of the water, because we then get that water up through wells and we use that water in our day-to-day lives. So now we're just going to look at what causes water hardness. So if we're looking at temporary hardness to begin with, in the atmosphere we have carbon dioxide as part of our air, and we also have our water vapour in the clouds and the evaporated water. And they react together to form carbonic acid, and that's our acid that can fall down as acid rain. And when that acid does fall down as acid rain, it will react with calcium carbonate, which we know as limestone, and they react together to form calcium hydrogen carbonate. Now, bicarbonate is just the old name for hydrogen carbonate. And that calcium hydrogen carbonate is now part of the water table, which we take up through wells, and that's the water we use. So that water now has temporary hardness. Now, how do we remove temporary hardness? So we know from our definition that it can be removed by boiling, and we're going to look at what boiling does to it. So if we take our calcium hydrogen carbonate and we apply heat, what gets produced is calcium carbonate. So this is our limestone again, but this precipitate, now it is a precipitate, it comes out as a solid, we call this lime scale. So you'll see that inside your kettles. If you ever cracked open a pipe or something as well for your heating, you'd see that inside. It's that white coating that's inside of your kettle. And that's lime scale. What also gets produced is some carbon dioxide gas and some water. And you might notice that this equation is actually the previous equation of how to create temporary hardness, just in reverse. So by applying heat, we're reversing that reaction to go back to what we began with. And now the calcium is now, after precipitating out as lime scale, so it's no longer in the water. The water no longer has any temporary hardness in it. So why are we concerned about hard water? So if we look inside a boiler, inside the boiler you can see that these have been damaged due to limescale deposits. That white coating on the inside is all limescale, and it can damage the boiler. So by heating up that water, we have removed all of the temporary hardness, but the limescale that got produced has built up and it has broken the boilers. Just like inside the pipes for the heating system, we can see that there are limescale deposits in here that have built up that will end up blocking the pipes and causing damage to the heating system in the house. Now, permanent hardness, so it's different because it cannot be removed by boiling, and that is another definition for us. So permanent hardness on the front of our flashcard, and on the back of the flashcard we have hardness that cannot be removed by boiling. And what causes permanent hardness is not hydrogen carbonate anymore, because that was only for temporary hardness. For permanent hardness, it's caused by the presence of chloride ions with the magnesium or calcium, or sulfate ions with the magnesium or calcium. And the reason why they can't be removed is because boiling them doesn't break them down. Boiling them does nothing to them, so that hardness in the water will stay, which is why we call it permanent. So far what we should be able to do is we should know our definition for hard water, our definition for temporary hard water, definition for permanent hard water, and what causes them. So what chemicals are involved. So for our temporary hardness, we have our calcium and magnesium hydrogen carbonate, and for our permanent hardness, we have our calcium and magnesium with either chloride or sulfate. So let's look at how we can remove water hardness. Now, one way we can remove it, the first way we're going to look at, is through something called ion exchange. So the ions present are those calciums and magnesiums, remember? So what we'll do is exchange them for other ions that don't produce hardness. So we have our calciums dissolved in our water, and we have this resin, basically this plastic resin inside a tube. And attached to that plastic resin are sodium ions, which don't cause water hardness. And when the water that is hard, that has calciums, is passed over this resin, the calciums and magnesiums get swapped for sodiums. So the calcium and magnesiums end up being attached to the resin, while the sodiums now flow out with the water. So the water is no longer hard because the calcium and magnesium is gone and has been replaced with sodium, which does not cause water hardness. So our calcium flows in, it meets our resin, which has sodiums attached. Then the calciums swap place with the sodiums, and our sodiums flow out with the water, so the water is no longer hard. So our second method to remove hardness in water is going to be by deionizing the water, so that we have deionized water, which is a word we're all familiar with using now at this stage. And what deionized mean is that all of the ions have been removed, whether they're sodiums, potassiums, calciums, magnesiums, sulfates, chlorides, nitrates, hydrogen carbonates, all of those ions, they are all gone from the water. And to do this, what we end up using are two different resins. So we have a cation exchange resin, which is going to exchange all of our positive ions. So whether this was a sodium, a calcium, a magnesium, anything positively charged, it will replace them with H pluses. We also have an anion exchange resin, which is going to replace all our negatively charged ions. So whether it's a sulfate, a chloride, a hydrogen carbonate, anything negative at all, it will replace this with OH minuses, and those H pluses and OH minuses will combine together just to form water molecule. So water flows through with all of these salts dissolved, and what comes out the other side is just pure water, nothing else. As a chemical equation now, to look at the positive exchange first, the cation exchange. We have water flowing in that has positive ions dissolved in it. We have our resin with our H attached. The ions exchange with the hydrogen so that our positive ions are now attached to the resin, and we get a H plus flowing out. On our anion exchange resin, where our negative ions get exchanged, we have water with our negative ions inside it. We have our resin with our OH attached to it, and they swap places. So we end up with the negative ion attached to the resin, it gets left behind, and what gets released into the water are OH minuses. And as we know, as we've seen in the last slide, the H plus and the OH minus then combine together to form pure water. So we get pure water outside the other end of the deionizer. Now we have a deionizer in the lab. I might have shown it to you once or twice before. If I haven't, I will, if and when we ever get back to see it. So we have these two different things. One is called deionized water, one is called distilled water. Now, deionized water we've looked at in the previous slide. It's when we remove all of the ions by exchanging them for H pluses and OH minuses, and we get pure water. Distilled water, on the other hand, is purified by distillation. We boil the water, and all of the ions, all of the salts get left behind, and then we condense the water again. And when we condense it, we end up with pure water. But one of them is more pure than the other one, and it's distilled water that is more pure, because distilled water has all of the gases removed as well. So there are gases dissolved in water, like oxygen gas, and that's what aquatic life uses to live. It's not the O's in H2O. There are actually O2 molecules dissolved in the water, and they're used for respiration. When we distill the water, when we boil it and recondense it, all of those gases are gone, along with all of the ions. So it's really, really pure. There is just H2O and nothing else there. Whereas when we deionize the water, what we looked at in the previous slide, yes, we remove all of the ions, all of the salts, but the dissolved gases stay in that water. So it's not quite as pure, because the dissolved gases are still there. So deionized water is less pure than distilled water, because distilled water has the gases and ions removed, whereas deionized water only has the ions removed. So now, what we should be able to do so far: explain how deionization is achieved using ion exchange resins, so that's those equations. Describe a test that can be carried out on scale deposits in a kettle. Now, scale in a kettle, that lime scale is calcium carbonate. If we want to test for calcium carbonate, what we do is we add HCl, and when acid hits a carbonate, it will fizz. Okay, so we'll get effervescence, or a gas is evolved. And that gas, if it was a carbonate, if it was limescale, should be carbon dioxide. And the way we can test if it's carbon dioxide is bubble it through lime water, and it should go milky. So that's how we test to see if there is a scale deposit in a kettle. We should also be able to describe how hardness can be removed by boiling, so that's removing our temporary hardness, and by ion exchange, that removes total hardness, removes everything. And we also need to be able to account for the purity of deionized and distilled water, so which one is purer and why. Now, don't mind this homework that's here. Your homework will be uploaded onto Teams. You'll see it as an assignment. It'll have a due date and everything. And when you look at that assignment, you can upload the pictures of your work from your copy there. It should be handy enough to do. I'll have a picture up of what the work is, not just telling you which book and which page, just in case you don't have the books with you at home. Use the chat feature on Teams to ask me, anyone else, any questions, even if it's not to do with the homework, even if it's just something you didn't understand as I was talking through it. Make sure you keep in contact. You're asking me everything that you usually would ask in class. We'll try and keep this as normal as it can possibly be.